Okay, so hello. Today I will continue the second video in this series, which is on the fabrication of MOSFET, or more specifically, I'll be going through the fabrication of a CMOS kind of device. So this will be the overview of what I'll be covering today. Firstly, the non-technical summary. Secondly, an overview of CMOS fabrication. Thirdly, a summary of fabrication techniques. And lastly, trends in MOSFET design. So first, for the non-technical summary. So you may have heard about computer chips, about CPU, GPU, but how are they actually made, right? So within a single computer chip, there is a very complex architecture of circuits consisting of semiconductors, insulators, and metal conductors of electricity. And so some of these features are extremely small. For example, this one over here shows um, a, a zoom in microscopy image of what a transistor looks like in such a chip at maybe in the nanometer kind of scale. So these are extremely small, thinner than a width of hair. And therefore, to make such small complex devices, right, semiconductor fabs are big, complex um, factories, right, with many equipment, each of them playing different roles to create this chip. Some of them may put down the insulating material, some of them may put down the metal material, some of them may put down the semiconductor material. And so within a semiconductor fab, there are hundreds of machines, and for a single semiconductor chips, there can be hundreds of processors as well. And so each of these processors will, for example, take place in one machine, right? And different companies make different machines. So you may have heard about companies like Lam Research, like Applied Material, and you may have heard of ASML, a very famous company in the semiconductor industry. So these are companies that make such equipment that are used to make every single computer chip that you find in your smartphone, in your computer, and even in like your washing machine. Okay, so that's the end of the technical, non-technical summary. So as for the technical content, I'd like to recap what we have gone through in the last video. So in the last video, we've gone through the case of an NMOS, how it looks like and how it works, how it behaves. And so PMOS, for example, is extremely similar. So this is an NMOS where the source and the drain are N-type regions, and the channel in between them is an N-type channel of electrons. So in a PMOS, right, is the opposite. So it's a P-type source and a P-type drain is a channel of holes that is formed, and the body is a N-type material. And so in order to turn on PMOS, right, instead of applying a positive gate voltage, right, you will apply a negative gate voltage. So um, in many semiconductor chips, right, we have what we call a CMOS structure, which consists of both the PMOS over here, as you can see, and the NMOS over here, side by side, connected to each other electrically. So today we'll be focusing on a rough outline on how like a structure similar to this is fabricated. So as you can see over here, the we have the N well of the PMOS and the P well of the NMOS, and in between them, right, we have something like a spacer. It's an oxide. We call this isolation. Why? Because we do not want like the electric fields, for example, of the PMOS and the NMOS to interfere too much with each other, right? So we do want to isolate the PMOS from the NMOS, and we do that by separating them, isolating them with a non-conductor of electricity, in this case oxide, which is always referring to silicon oxide. Okay, so to do that, we first need to etch, right, trench in the bulk material. You need to etch a trench. And so, however, we need to kind of define where we want to be etched. Right? Etch is just a material removal. Right? We want to define where we want to etch and where we want to preserve the material. So basically, the location of the etch is defined by a mask, right? A kind of a mask that is consisting of basically nitride and in this case a photoresist on top, and the pattern is created by a process called photolithography. So you may or may not have heard of this idea of lithography, which is actually a very old technique of like creating patterns or images on a film, right? And so photolithography in semiconductor technology is something similar. Is using, like in this case, a way of exposure to light to create a pattern on the surface of a material. So in this case, we are creating a pattern on nitride, right? And in turn, we are using that pattern on the nitride to etch a pattern, or we call a trench, in the silicon material. And so you may see here that there's this pad oxide. So just for your information, this is to reduce the stress at the interface between the nitride and the silicon layers, because if you know a bit of material science, the crystal lattice of nitride and the crystal lattice of silicon. So when I say nitride, I mean silicon nitride. So basically the lattice parameters of both material, there's a large lattice mismatch, which causes basically strain at the interface, and the pad oxide helps to relieve that strain, right? Thus preventing things like delamination or like defect formation at the material's interface. So now after we have formed that trench, right, it's time to fill it up. Right, so the previous photoresist over here. So photoresist is a polymer kind of material. Polymers are organic, so to remove them, we combust them. But in this case, we call this a plasma ash. So essentially, it's using an oxygen plasma to burn off. You can think of it as burning off the photoresist. And so it leaves behind the nitride, they're still there, and we grow oxide in all of these spaces. So what they normally do is that they grow a thin layer of liner oxide using thermal oxidation. Because remember, this green area is silicon. Silicon can be oxidized thermally in an oxygen containing ambient to form basically a thermal oxide layer. And then the entire trench is filled with more silicon dioxide using what we call chemical vapor deposition, CVD. So it's a way in which material can be deposited on the surface by through the means of a gaseous on a surface rather chemical reaction between certain gaseous species, right, that happens on the material surface. Okay, we'll cover like techniques such as CVD and photolithography, of course, in more detail in the subsequent videos of this series. Then, as what you can see over here, right, there's a thick layer of silicon dioxide that is like existing at the top of our wafer currently. So what we want to do is we want to polish it down, and so we use something called chemical mechanical polishing. It is actually pretty similar to how we polish a knife blade. If you have done that before, right? Polish a knife at home, right? Cooking knives. What you normally do is that you rub it against a very rough surface, and sometimes you add like a fluid to lubricate it, right? So chemical mechanical polishing is something similar, where we use basically a pad, right, a surface that has a lot of basically roughness, right, roughness to polish down the surface. But there's also a chemical component to it, in that the slurry, there'll be a slurry that will contain chemical components that can help to chemically remove, in this case, the oxide that we're trying to remove as well. So in this day and age, right, this technology is able to achieve extremely good planarization of the surface. That means the surface becomes very flat, very planar. Okay, so and then how does it know to stop here, right? Because the nitride material is very much harder to planarize than the oxide layer, and so the CMP machine is able to sense this change in the amount of like resistance, right, that it is facing, and is able to stop the planarization polishing process. And so after that, we can use basically hydrofluoric acid, hydrogen fluoride, basically to etch the remaining oxide in these gaps over here, and basically phosphoric acid is used to etch nitride. So these are extremely selective reagents. So hydrogen fluoride is extremely selective to oxide, so it etches oxide at a much higher rate than it etches other materials like nitride, like silicon material itself. And likewise, phosphoric acid is also very selective, in this case selective for nitride, and it doesn't etch oxide that much compared to the rate at which it etches nitride. Okay, so eventually you get a very flat surface of the oxide, which acts as the isolation. You see over here, the isolation. Right. So okay, now it's time to form your P and N well formation. So boron implant is used to dope the P well for the NMOS device. So remember, the NMOS has a P bulk, a P well has a bulk. Okay, and conversely for the PMOS. So the pattern, once again, right, where to put the boron in and where not to put the boron in, that pattern is defined by photolithography. So the thing that is blocking is what we call a photoresist, which we'll cover. In fact, I think we'll cover in the next video. So, and the phosphorus implant likewise is used to dope the N well for PMOS. So what we call as implant, basically, these are called ion implants or ion implantation. So basically what we are doing is that we are accelerating ions at very high speeds, or at basically high enough speeds depending on your requirement, to penetrate and into the material and occupy sites in the material, right? Occupy substitutional sites, to be more precise, in your silicon material. So yeah, that will help to achieve the doping that we want. So normally ion implantation is the default method of doping for most semiconductor processes, right? Not all, right? Some semiconductor processes still use other forms of doping, but ion implantation is one of the major methods nowadays. Okay, so this is followed right by annealing, because normally what happens is that this kind of implantation of ions, these ions are high in energy, right? So they come in and they tend to cause damage to the silicon structure. So annealing helps to heal that damage. So annealing is normally heating up the wafer to a certain temperature, and that helps to heal the lattice structure. At the same time also, when we implant ions in the material, they may not occupy substitutional sites. And if they occupy like interstitial sites, they are not electrically active. So we need to anneal it to ensure they jitter over and occupy the substitutional sites in the lattice of silicon, and that is only when the dopants are considered to be activated and you can say they're electrically active. Okay. So next what we will do is that we will form a temporary gate. So this is a temporary gate, right? It's made from polysilicon. In this day and age, right, in modern semiconductor devices, polysilicon is not conductive enough to be the actual gate, right? Polysilicon, if highly doped, can be a conductor, but it still has a fairly high resistivity compared to metals. So this gate is not here to stay. It's there temporarily. Then you may ask, right, if it's there temporarily, what is its use at all? So its use actually is to define certain features later. Okay, but basically how this polysilicon gate is created is that basically a uniform conformer. So when I say conformer, means it's like uniform in thickness, right? A polysilicon layer is deposited. Then after that, right, lithography and etch is used to etch away the segments that you do not want, to leave behind these like small cubes kind of patterns. Right, this kind actually it's not really cubes lah, because this is just a two-dimensional cross section. It's more like maybe a line or something like that. But basically, lithography, right, is used to define the pattern of where to be etched away. And after the etch, we leave behind the two polysilicon gates, one for the PMOS, one for the NMOS. And then after that, we do a quick oxidation of the surfaces of the polysilicon gate. This can be done with thermal oxidation. Since polysilicon is silicon after all, it can be oxidized into silicon oxide. And so, as what I said earlier, this temporary gate is to allow the defining of the locations of the source and drain regions for subsequent doping via implantation, which you'll see very shortly. So the next step is for the halo implant. So what is the purpose of the halo implant? Well, it turns out that one major form of leakage current in basically MOSFET devices is what we call punch-through defect. So this occurs when, right, the depletion region, remember there's a depletion region at the source and drain between the N and the P regions, and here the N and the P region. So there is a depletion region. So when your gate size or channel width, to be more specific, your channel width gets smaller and smaller and smaller, your channel length gets smaller and smaller and smaller, which is the trend in more and more advanced technologies, right? So basically when it gets smaller and smaller, what it tends to happen is that the depletion regions at the source and the drain tend to overlap. And when they overlap, basically there is a tendency of a punch-through leakage current happening, right, between the source and the drain. Okay, so there is even when the device is in the off state, that means when the gate voltage is lower than the threshold voltage, and so we want to avoid that from happening, because it degrades the device performance, right? That means there's leakage, there's current flowing through when the device is supposed to be in the off state. That is not desired. So what we do is that we do a halo implant. So halo implant is an implant that like intensifies the doping concentration in the P wells of the NMOS, for example, and the N well of the PMOS, right? So remember what I said earlier in the previous video, that higher dopant concentration makes the depletion region width narrower. So that's the point we are doing here. We are doping the wells more with a higher concentration of dopants, so that the depletion regions will be smaller. And when the depletion region is smaller, that means my channel width can shrink without the depletion regions overlapping and causing punch-through current. Okay, so so for the NMOS, we are wanting to intensify the doping in the P well, so we use boron, a P-type implant, and as for the basically the PMOS, right, we use an N-type implant for the halo implant in the N well of the PMOS. So each time, right, a photoresist is used to mask the other side that we don't want to implant. And note that this halo implant often occurs at the angle to the surface because we want it to kind of be somewhat in between the source and the drain, in the somewhat close near the channel region, where the channel will form. So that's why the ions need to enter the material at an oblique angle. Okay, so next is LDD doping. LDD doping, the concept is somewhat different. You may even think it's contradictory to halo doping. So when halo implant, we are trying to intensify the dopant concentration. LDD stands for lightly doped, right? Lightly doped. So actually, what we are doing is that basically, for example, the NMOS, right? The source and drain is N-type, right? And strongly N-type. Why it must be strong? Because we want it to be highly conductive, because source and current passes through the source and drain. So we often indicate it by for example N plus. So it's highly N doped, right? However, the problem is that when we have a highly doped N-type material, right? Remember what I mentioned in the last video, where high dopant concentration result in large built-in voltage. Large built-in voltage in the p-n junction result in a high electric field, right? High electric field, it will accelerate electrons very quickly. And even though it may sound like a good thing, it's not exactly a good thing, because when you have high electric fields accelerating electrons, we have what we call the hot carrier effect. So these electrons become very energetic, right? Somewhat hot. You can think of it as hot, very energetic, because they're accelerated through this very high electric field. And when they're very energetic, they tend to cause damage along like the paths at which they travel. And at the same time, if they're very energetic, they can undergo leakage, current leakage to places where they're not supposed to go. Because they have so much energy, they can like cross over like paths that are otherwise quite resistive to, let's say, electron flow. So we don't want that. So basically, we do a lightly doped drain. So it's like N minus region next to the N plus region of the NMOS. So we do this so that it will not immediately be the N plus region in contact with the P well, but more like the N plus region, then the N minus region, then the P well. And so this kind of like relaxes, makes the concentration gradient, and as a result the electric field gradient, right, more gentle, right? It makes it more gentle. So when it's more gentle, the electric field is less strong, and if the electric field is less strong, the hot carrier effect is mitigated. So for the NMOS, right, we doped lightly some arsenic, which is an N-type dopant. For the PMOS, we doped lightly some boron. Okay, so normally this doping is very shallow, so it is done at a lower energy, and normally at a lower ion concentration in the ion implantation. Okay. Then next, we want to have a sidewall spacers. Why sidewall spacers, right? Okay. But basically, how we do this is that we have a conformal layer of oxide deposited with chemical vapor deposition. Then we use the anisotropic etch to etch the vertical direction. So only like the etch happens only in the vertical direction. So anisotropy means different in different direction. So in the vertical direction, this etch is very effective, but it doesn't etch the horizontal surfaces. So as a result, the horizontal surfaces here next to the temporary gate are preserved, and we call these sidewall spaces. So what is the purpose of these sidewall spaces? It's used to define a dimension smaller than the resolution of lithography. So remember, I told you that lithography is the primary way at which you basically create patterns on the wafer. But lithography, as you'll see in the future video, has a resolution limit. So you can't define patterns clearly smaller than that dimension limit. So, however, using the sidewall spacer method, we can define features that are smaller in dimension than the resolution of your lithography systems. And so why are the sidewall spacers there? I didn't fully answer that question yet, right? It's so that when we dope the source and drain now, it is displaced left and right from that lightly doped drain. Because imagine if you dope these regions as lightly doped, and then you doped the highly doped source and drain on top of it, that defeats the purpose, right? We want the highly doped source and drain to be laterally displaced a small amount from the lightly doped drain regions at the source and drain. So basically, these CMOS spaces help to do that. So now we can form the source and drain with ion implantation. So once again, the arsenic implant, N-type implant, used to form the source and drain of the NMOS, whereas your boron, which is a P-type implant, is used to form the source and drain of the PMOS. So so in this case, the implantation will be higher in energy because you want to get a deeper, slightly deeper implant than the LDD region, and it will also be basically higher in the intensity, in the concentration of ions that you're putting it in. Okay, then after that, don't forget, whenever we dope something with ion implantation, the annealing step is uh, absolutely necessary. So in this case, we do what we call a rapid thermal anneal, also known as RTA. So why the need for rapidity? Why the need to be so rapid? Right? Why this need to be so fast? This is because, right, the ion implantation, especially at the high dose and high energy that we are doing over here, will cause ion damage in the silicon lattice. And when there's ion damage in the silicon lattice, a phenomenon known as transient enhanced diffusion occurs. So if you slowly anneal, the basically your dopants will be diffusion will be enhanced by TED, and basically the dopants will run to places you don't want them to run to, right? So by using the rapid thermal anneal, we do the anneal very fast. The dopants don't have time to move to places where it shouldn't move to, and we basically have very nice profile, right? An ideal profile that we want, that will achieve the best device characteristics. Okay, then the next step is finally we get to form our metal connects. So remember that this is an electrical device. We do need to connect our source, drain, and whatsoever to basically the general circuitry of the board. Okay, so what we do is that we want to form the electrodes of the source and drain, because the gate is not yet done, right? So first the source and the drain. Then what we do is that we deposit titanium, right, to form the contacts. However, what we do is that we then heat to react titanium with silicon to form conductive titanium silicide. And so it looks like it's a non-conductor, right? It's like a ceramic kind of thing, right? It's basically a metal and a non-metal, but no, actually this is a conductive material. So it's very good as a conductive contact to later contact with the metal circuitry, right? The metal interconnects. So and we have to do this annealing to form the silicide to ensure good adhesion to the silicon surface. Okay, and the unreacted portions can then be etched away, right, using an etch that is very selective against. That means it does not really etch the silicide, but etches the unreacted titanium away. So then after that, what we do is that we fill up the remaining empty spaces with oxide, right, silicon dioxide. Once again, if CVD is a very good way to grow SiO2. In fact, you'll learn that CVD itself has many different methods, like atmospheric pressure CVD, which is not really used nowadays. Low pressure CVD is still quite commonly used. Plasma enhanced CVD, very commonly used, right? You'll learn that all in future series. But anyways, SiO2 is deposited by CVD and then planarized with CMP. And then finally, we can get rid of a temporary polysilicon gate because its purpose has been completed. Time to put in the real gate oxide and the real gate. So basically, we are preparing for high K gate oxide deposition. So now it's time to put in the high K gate oxide. So what is high K, right? So basically, earlier we talked about the gate oxide being like things like silicon dioxide. However, the problem with silicon dioxide is that its dielectric constant is not particularly high, and as a result, right, to get a high gate capacitance, we need a very thin layer, right? Because you know the equation for capacitance, right? The thinner your dielectric layer, right, the higher the capacitance. However, the problem with your oxide layer being too thin is that there tends to be leakage current through the oxide, and the oxide can be easily damaged when you apply a bit higher voltages, right? There can be breakdown, what you call electrical breakdown of the material. You probably learned about that in secondary school when like the fuse blows, right? That's an example of electrical breakdown. So if your oxide layer is too thin, right, it tends to encounter this problem. So the solution is to use high K dielectric, which is basically dielectric materials with a much higher dielectric constant. So that means I can have a thicker layer, right, but yet still having very good, very high capacitance. So one example that's commonly used, right, in industry, right, is hafnium dioxide, HFO2, right. This is widely known to be a very good high K dielectric for basically gate oxide material, widely known. So yeah, what we normally do is we use atomic layer deposition, also known as ALD, right? Because we want to achieve very thin, maybe just a few atoms thick kind of layers, right? Sub nanometers maybe, normally sub nanometers kind of layer quite often. And so yeah, we do that to achieve the very thin layer deposition. So but as you can see here, right, the ALD is used to deposit not just your HFO2 but also your TiN again, and aluminum. So in this case, TiN and TAN, right, so titanium nitride and tantalum nitride, they are conductors, and they are there because their work function, right, differs from that of the main contact aluminum, and that work function is able to modify the threshold voltage. Because sometimes the, like let's say you want the chip to have a certain threshold voltage, right? This is based on your circuit design. Maybe you want, based on circuit design, you find that this threshold voltage is very good for your purpose that you want the chip to be used for. However, right, you want a way to modify the gate to achieve the threshold voltage. So one way is to by depositing layers of TIN and TAN of varying thickness, and it can basically like achieve kind of like a threshold voltage kind of modulation. And so eventually aluminum is used as the final gate contact. Okay, so the good thing about ALD is that you can basically very cleanly deposit all of these layers without removing the wafer from the vacuum environment that ALD is conducted in, right? Because ALD you can switch the source. So like I use a hafnium source for HFO2, then I use a titanium source, then a tantalum source, right? And then I change the gases that I pump it in from oxygen to nitrogen and whatsoever. So I can achieve like this sequential layering of very well-defined thickness of materials without breaking vacuum. And that's very important because some of these layers are easily oxidized. So if I, let's say, break vacuum, take it out of the vacuum, then put it back in, and I expose it to air in the process, right, these very thin layers can get oxidized. And when we have things like electrical contacts there, we definitely do not want any oxidation, because that increases the contact resistance, changes the electrical performance of the device and things like that. Okay, so then the next is to do the gate contact. As I mentioned before, right, it tends to be aluminum. It can be aluminum, right, although it also can be other metals, right? But in this case, this example is aluminum, so it's deposited with PVD, physical vapor deposition. Another word for it is sputtering deposition, which we'll learn more about this in the future video in this series. And then once again, CMP is our useful tool in helping to planarize the surface. And okay, finally we can begin on what's called the back end of line, which is BOL. So our device, which is our transistor, is finished. So you can think of all the semiconductor related processes as being kind of done. And what is left is connecting the device to the back end of the chip, right? Where you have, if you've seen the computer chip before, all your studs, right? Your studs that basically connect to your eventual PCB and your eventual motherboard and things like that. So yeah, time to connect the device to the back side of the chip. So what we do is that in this case we first etch a via. So a via is basically like a trench, so called somewhat of a trench, and we fill it up with tungsten, which is conducted using sputtering, PVD once again, and CMP once again are useful to planarize the structure. And so this is actually what is commonly known in industry, or basically in research, as well as the Damascene process. So the Damascene process has basically three simple steps. A via is open, etched open, right? The metal is filled into the via. What method is filled in doesn't matter. Can be PVD, can be electroplating, can be CVD, right? But basically the metal is filled into the via, and then after that the surface is planarized. So these three steps is called the Damascene process. So then after that, we tends to use copper as the interconnects for like the back of the chip. So why copper? Because copper actually has a very low resistivity, and even though aluminum used to be the leading contender, however, basically copper has certain favorable properties which we may cover in future. Favorable properties such as like low electron migration, things like that. But yeah, I won't go into that in this video. But basically, copper is commonly used as interconnect. So we do once again another Damascene process. In fact, this is commonly called a double Damascene process because we etch two things, right? The trench and the via. Trench is the wider thing over here. Via is a narrower space over here. So sometimes it's called the dual Damascene process. So basically, we etch the trench and the via. Actually, there's quite a bit of technique that goes into etching the trench and the via. Because after all, it's not just a straight line down, right? You have to get this a profile, which I may cover in a future video, I may not, but definitely not in this video. But there's some technique to achieving this profile in the dual Damascene process. But basically, this profile is created. Wait, first the interlevel dielectric, right? This dielectric is created first using a CVD. Then after that, the trench and the via is then etched. Okay. Then after that, copper is electroplated. Okay, so copper is normally deposited by electroplating process. Then after that, the surface is then planarized using CMP. So actually, this idea of CMP, chemical mechanical polishing, became really important when they started using copper in place of aluminum as interconnects, right? And this is because copper is extremely difficult to etch. Because one main point of etching is that when you etch something, you want the byproducts to be volatile, so that it will not fall back on your wafer, it will just go away. And the thing is cleanly etched away, the material is cleanly removed away. Right? However, for copper, right, every etch chemistry, right, results in non-volatile byproducts that will fall back on your wafer and contaminate it. So it is basically, copper is not able to be etched in the same way as aluminum. And that's why CMP technology really became very important when copper was used, because CMP is the only way to remove copper from the surface, right? By physically and chemically, right, polishing and like grinding it away. Yeah. So even though like the device seems to be like the most complicated part of the process, and in many ways it kind of is, but the back end of line is also a very complex process, right? Because we have many layers of metals. We normally call like the closest layer to the device as M0, then we have M1, M2, M3, whatsoever, and then your final, layer, and then your passivation layer on top of it to cap and protect the metal from oxidation, because copper oxidizes quite easily. So as you can see in this image over here, all these lighter colored things are the metal. So as you go higher up, the pitch, which is the distance between the metal interconnects, get bigger and bigger, right? But there are many layers of the metal, so it's not a trivial process to be able to ensure that every layer is aligned, because once there's any misalignment, right, there can be an open circuit and the device will fail. So okay, now we are reaching the end. I said that I will cover an overview of device fabrication techniques, right, the processes, but I kind of forgot to include in the slides, so I guess I'll cover that in the next video. But maybe I'll shortly, very quickly rather, cover trends in MOSFET architecture. So these trends means like the direction in which it's progressing, or the directions in which it has already progressed in many ways. So what we have seen earlier is the planar field effect transistor. So we have your basically so this is basically in the opposite direction that we saw in this in all of the previous images, right? It's in a different direction. So your source is here, your drain is behind here, and your gate is over here. So your channel is below the gate, right? It's between the source and the drain, right? So this is what you call the planar architecture. Why? Because your source and your drain and all is basically a two-dimensional surface lah. Your channel is a two-dimensional kind of surface within the bulk, right? Within the bulk. So it's like, yeah, there's nothing jutting out. However, for the FinFET, right, the FinFET is that the channel juts out. The source and the drain and the channel is a protruding kind of fin lah. Basically, we call it a fin because it kind of looks like a fish, the fin of a fish. Okay, yeah. And so, what is the good point of this, right? Because we see that in the planar transistor, the contact between the gate and the channel is only this square over here, so it's like a single surface. However, for the fin, right, you see three surfaces, left, right, and top of the channel is in contact with the gate. So what happens when you have that is that the gate is able to be better controls the channel. So that means the gate voltage is being able to be better applied to the channel. So what happens is that this means that we can regulate the turning on and turning off of the channel much more effectively. So yeah. So physically what this means is that we tend to have like lower, let's say, subthreshold leakage current, right? Better subthreshold swing, because it's easier to turn on the device, right, when we have more surfaces of the gate in contact with the channel to turn it on, right? So it's very favorable electrical properties, characteristics of a FinFET device. So FinFET architecture was first introduced, if I'm not wrong, by Intel in their process nodes that is below 20 nanometers. So basically that's like the channel length of below 20 nanometers. Then they introduced the FinFET technology. So the reason why they introduce it at smaller channel lengths is because as channel length gets smaller, it's harder and harder for the drain to control the channel without having things like leakage current, punch through current, right? Poor behavior in the subthreshold swing, things like that. However, when we introduced the FinFET architecture, right, Intel was able to downscale their channel length to below 20 nanometers, like 17 nanometers, things like that, and still maintain extremely good electrical properties. And so, if right, like changing the surface in contact from one surface to three surfaces is so good, right? Logically, you would say, what about four surfaces? What have the gate all around the channel, right? And that is precisely the idea of the gate all around FET, right? GAA FET. So this is the case where the channel is basically completely surrounded by the gate. So 1, 2, 3, 4 surfaces are in contact with the gate. And yeah, and theoretically that would result in even better device performance, right? And so from what I know, right, there's available information, obviously. Samsung is using the gate all around architecture for their 3 nanometer process nodes already. Right. However, of course, the device is much more complex, right, compared to FinFET, because we have this like suspended channels, right, with like what is below it, right? How do you get this kind of edge pattern, right? There are many more complexities, right, related to device fabrication than your FinFET and the planar FET. Okay. So that's it for this video. So in the next video, I think it is appropriate to start our processes with lithography, because that is the main way to define patterns in microfabrication. Most other processes rely on lithography to define the pattern on where it is to be carried out. We cannot choose where to etch without lithography. We cannot choose where to implant ions without lithography, right? We cannot choose where to deposit things many of the times without lithography, right? So lithography is possibly one of the most crucial processes. Actually, every process is crucial, but it's a really interesting and very important process in semiconductor fabrication. So I'll be covering that immediately in the next video. Okay, so I guess that's the end of this video. So I hope that I didn't make any mistakes. I hope that it was an enriching video and that you all learned something about semiconductor fabrication, right? If you don't understand a lot of the details, don't worry, because I'll cover them in greater detail in the subsequent videos. But hopefully you all could appreciate a more bird's eye view, a more like a broader view of like the entire fabrication process that you would encounter in a semiconductor fab. Okay, so thank you everyone.